Okay, perfect. Let's move on to another application. Again, we want to do high resolution, high fidelity natural image generation. A little bit of the background, you have a generator, you have a discriminator. This is going to help me write down the notation. This is your loss function. For GANs, you have some latent variable. Your latent, you're sampling it from normal or uniform. So this is not conditional. This is unconditional. That's why you need to have a noise. Now we want to introduce BigGAN. We want to scale it and generate realistic looking images, high resolution. This is an engineering paper, so there's going to be a lot of details that I'm not going to be able to go through, but I'm going to be able to tell you the highlights. But the moral of the story is that you're going to have a larger model and larger batches. One of the techniques is self-attention GANs. I'm going to go through that next session. So don't worry about the first item. If you don't understand it, it's a GAN that you're changing the architecture. We are going to use hinge loss, and we saw that you can actually use hinge loss, and you are going to provide class information to your generator. Now your data are going to be ImageNet type data, and then you're going to have millions of data, and you're going to have thousands of classes. So it's going to be a good idea to condition on your labels. But the way that you're going to condition on them is different here. You can actually, if you remember in batch norm, you had two extra parameters. One was rescaling after the normalization, and one was adding a bias. So this is how you're conditioning. You're changing your batch norm. But for the discriminator, you're going to provide the class information using those one-hot vectors and doing the projection. Projection is matrix vector multiplication. So you can think of them as word vectors. And then you're conditioning, you're putting that as an extra input to your discriminator. We are going to do a spectral normalization on the generator. We just learned about it. And for the generator, we also learned about moving averages. So you keep a moving average of the weights of your generator. And then that's what you're going to use for generating images in production for evaluation. And then in terms of initialization, you're going to do orthogonal initialization. So your weights, you're going to initialize them in a way that they are orthogonal. There is another trick, the truncation trick, that is going to help you generate images that look more realistic. What is the trick? You can train using Z's that are sampled from normal. But then in generation, in production actually, you're going to truncate your normal distribution to be in an interval. We sample from truncated normal. What are the trade-offs? This is going to improve individual sample quality. So the quality of your images are going to improve, but there is a cost to it. You're going to reduce the variety of the images that you're going to see. And this trick only works if you have orthogonal normalization. I'm going to tell you what that is. If you don't do it, and if your model is any other model without orthogonal normalization of the weights, you're going to see some artifacts, some saturation artifacts. For instance, the eyes of this dog is messed up. The colors are messed up in the background, etc. So you're going to do orthogonal regularization during training. You're going to add this to your loss function. You're going to say that my weights need to be orthogonal, but then you're removing the diagonal of that. So it's an approximation to your weights being orthogonal. What do you get? Let's study the effect of this truncation. If you increase the truncation, if you truncate more, it means that if you shrink the interval that you're truncating from 2 to 0.4, initially you have a variety of images of dogs because now you're conditioning on the class of dogs. So you're going to only generate dogs, but it's a variety of dogs. And then the variety is going to go down, but the quality of the images is going to go up as you truncate more. In terms of numbers, you can look at two numbers, Fresh inception distance and inception score. For fresh inception distance, the lower is better. So the lower is better. And for the inception score, the higher is better. And then these are different configurations, like what should be your batch size? What is the channel multiplier? How many parameters your model has? Because remember, larger batches, larger models. At what iteration you're gonna stop? And this is the score. But there is also another observation in this paper that I want you guys to know about. If you look at the top singular value of the weights in your neural networks, these are weights for different layers. You usually see the symptom of mode collapse, where one of those singular values is going to explode. So that's for the generator, and that's for the discriminator. It is exploding at this iteration. So the discriminator is less sensitive to that, but the generator is more sensitive. And that's why a spectral normalization is helping G. I think I'm going to stop here. And for those of you who have questions, I'll be around. And for those of you who want to leave, you can leave.